Imagine you have a 70 billion parameter language model. Each parameter is stored as a number. If those numbers are stored in float 32, each parameter needs 4 bytes. The weights alone need around 280 gigabytes. That is the first reason modern LLMs avoid all FP32. It's not because float point 32 is bad, it's actually very convenient. It gives a good amount of precision, a large numerical range, and a stable behavior. The problem is the scale. At 70 billion parameters, every extra byte is multiplied 70 billion times. Now compare that with an ideal 4-bit representation. 4-bit is half of a byte. So if we calculate it for 70 billion parameters, it's now 35 gigabytes. Same parameter count with the same architecture for the LLM, but very different hardware requirement and very different cost. So when someone says this is 70 billion model, that's not enough information for you. The better question is 70 billion numbers stored in what format? Because a model's parameter count only tells you how many numbers it has, but the number format tells you how expensive those numbers are. And this is why modern AI hardware cares so much about BF16, FP8, INT8, INT4, or formats like NF4. To understand what are these acronyms for, we need to separate two ideas that often gets mixed together: precision and range. Precision is how much detail a number can represent. Range is how large or small the number can get before the format breaks. Floating point or FP32 gives you both. It uses 32 bits, and those bits are split into a sign bit, exponent bits, and mantissa bits. The exponent controls the range. The mantissa controls the precision. This is why FP32 is stable. It has enough exponent bits to represent very large and very small values. For a long time, FP32 was the safe default. But if you want to use it at LLM scale, safe became expensive. So the next step was FP16 or floating point 16. FP16 cuts the storage from 32 bits to 16 bits. That cuts the memory roughly in half. But FP16 has fewer exponents than FP32. That means its numerical range is much smaller. So during the training, large values can overflow or very small gradients can underflow. And this is why FP16 can be fast, but it can be also fragile. Then there is new proposal to solve this issue: BF16. BF16 is short form for the brain floating point 16, and it developed by Google Brain. And this is the key idea for it. BF16 keeps the same number of exponent bits as FP32, so it keeps almost the same numerical range, but it has fewer mantissa bits, so it loses precision. That trade-off is extremely useful for training large language models. Training often needs range more than perfect decimal detail. You can tolerate some noise in the lower bits, but if values overflow or underflow, training can break. BF16 gives you much of the stability behavior of FP32 while using about half the memory. That is why BF16 became so popular for LLM training. Now at this point, memory capacity is only one part of the problem. The other part is memory bandwidth. Modern GPUs are very good at math, but the math units need data. Weights and activations have to move from memory into compute units. If your number format is smaller, for example, you move fewer bytes. That means more values fit in cache. Less bandwidth is consumed and the hardware can feed the compute units more efficiently. This is why formats like FP8 exists. But FP8 is not simply use 8 bits everywhere. That would be too unstable, like the problem that we discussed before, overflow and underflow. FP8 is useful when the system knows where reduced precision is safe. Some operations can use FP8. Other parts still needs BF16 or floating point 32. For example, sensitive reductions, accumulations, normalizations, or master weights may stay in higher precision. This is mixed precision. The point is not to find the perfect format. The point is to use the right format in the right place, not finding the best ideal format that can resolve all the problems. Inference is different from training, for example. During training, the model is learning. So during training, gradients matters, stability matters, but on the other hand, during inference, the weights are fixed. That means we can often be more aggressive. Instead of storing weights in BF16 or FP16, many inference systems store them in integer 8 or integer 4. But this is exactly where quantization gets misunderstood. Quantization is not just taking every floating point number and rounding it blindly into a tiny integer. Actually, this is the definition of bad quantization. Good quantization asks where can the model tolerate the error, which values are sensitive, what scale should we use, should we quantize per tensor, per channel channel or per group. That is why methods like LLM INT8 or GPTQ, AWQ and NF4 exist. They are all trying to reduce memory while controlling the damage caused by lower precision. Modern LLM systems are not really low precision or high precision. They are mixed precision systems. It works because the system is careful about which precision is lost. Some weights can be approximated. Some outliers need protection. Some operations still need higher precision. This is why AI hardware vendors care so much about number formats. A GPU is not only judged by how many operations it can do, it is judged by which format it supports efficiently. For example, can it multiply FP8 quickly, or can it accumulate safely? Can it move integer 4 weights efficiently? Can it dequantize fast enough, or can the memory system keep up? At LLM scale, number formats are not just a software detail. They decide what hardware can actually run the model. Because 70 billion parameter in FP32 is totally different hardware problem than 70 billion parameter in BF, for example, 16. Or if you have 70 billion parameter in 4-bit quantized form, this is completely a different deployment story. At LLM scale, numbers are not just math. Numbers are memory. Numbers are bandwidth. And they're the compute throughput and they're the cost. And the reason modern AI avoids all FP32 is not that FP32 is useless or it doesn't have good precision. It is because using maximum precision everywhere is too expensive. And modern AI is about spending precision where it matters. So if you have experience using different precision with the same model, please share your experience in the comment down below and tell us, based on the hardware that you have, what kind of performance did you see from that model. Until the next video, good morning, good afternoon and good evening. Bye.